taken the dictionary definitions of work and energy. Now, obviously, worksheets are at the back if you haven't got them already. These definitions, gentlemen, are from a physical context. If you Google searched work, it might say what a person does from 9 to 5, Monday to Friday, as a source of income. Different type of work. The physical definition is the transfer of energy in a physical system. Okay, cool. So then you go, all right, what's energy mean? So you go through your dictionary and you look up energy. And it says energy is the ability to do work. You go, okay, cool. Hang on, what was work again? So you flip back through your dictionary, you go back to work. Oh, it's the transfer of energy. Can you see the problem here? In order to explain one, you need the other, and you get stuck in this definition loop. It doesn't really explain what the hell is energy, what the hell is work. So, can we just add a little addition, and this is sort of the year 8, 9 definition. It's also the ability to cause change. Okay? In a system. And that's kind of a very basic example. Energy is the ability to cause change. If a car has kinetic energy, it can smack into another car and that causes a bit of change. It's going to cause that one to speed up, it might bend it, it might break it. If you've got an object on a table and we say it's got potential energy, well, it's got the ability to cause change. It could fall off and then smack into something. Things are changing. We've got acceleration. We've got movement. Okay? Now, here is our equations. We can say that work is the transfer of energy. In fact, hang on, wait, hold on. This box is not big enough. I'm going outside the box now. We're going to go work is the transfer of energy. Now that triangle means delta. It means the change in. And whenever you see delta, it means final minus initial. Okay, now if your two energy values, if your final energy is different to your initial, then there has been a change. I could give you energy, in which case your final is greater than your initial, or you could give me energy, in which case your initial is bigger than your final. So just be careful. It depends on which way the energy is. If this is a positive value, then you are receiving the energy. If I give Miles a shove, he receives energy. Okay? Whereas if Miles is sprinting along the oval and I'm there out on yard duty and he spear tackles me and I go flying, then Miles' energy goes down and I get the energy. So you've got to be careful of who's getting the energy, who's losing the energy. And this is where we've got to add a little bit of English. There's also another equation that we can use, and that's F times S. So, let's write down a few things. F is force, which we've already learnt in newtons. S is displacement, which is in meters. W is work. And E is energy. Now we'll just leave those units for a moment. Now from this equation, we can look at the units. If I took the unit from force and multiplied it by the unit for distance, I would get the units for work. So as Jack was saying, the unit for force multiplied by the unit for distance is Newton times meter, and that comes out as Newton meter. However, we don't normally call it a Newton meter. We call it a capital J, which is a joule. Named after James Prescott Joule, a famous British mathematician and engineer. He was looking at how energy transferred between heat and mechanical energy, and he started measuring units, and it was called joules units. So that's why it's got the capital J, and he was obviously taking from the work of who? Newton. Very good. Now, a Newton is also a derived unit. You don't have, guys, this stuff here in the blue, and I should say this stuff here in the blue. The stuff in the blue is not part of the course, but it's useful to understand that a Newton is also a derived unit. If we took Newton's second law, F equals ma, right? Mass times acceleration. Well, I could say, well, a Newton, mass times acceleration, the unit for mass is kilogram. The unit for acceleration is meters per second squared. And if I multiplied that by another meter, okay, then we get kilogram meters squared per second squared. That's the true unit for energy. But I don't say that a candy bar has 4 million kilogram meters squared per second squares. That's a bit silly. I would say that the candy bar has 400 calories, or 8 million kilogram meters per second squared. Rather than saying, is it 800 kilojoules? 8,000 kilojoules. I think it's 8,000 kilojoules. Anyway, energy in joules. We don't say that unit. It doesn't really mean much to say something has that. Instead, we would say it's a joule. Okay? Not important. Next thing, gentlemen, you should hopefully have a little gap here. If your delta E, if it's positive, then work is done on the system. I go back to the example, if I just went over and gave Miles a big shove, then his final energy is greater than his initial, and we get a positive E, positive delta. Okay? That would mean that work is done on Miles. Okay? Whereas going back to the example, if I'm standing out with my hat and my frisbee and no one's playing frisbee with me, so I'm just standing there like a garden gnome, and Miles comes sprinting up and spear tackles me, you would say, well, Miles' his energy was high, and then he slowed down. Maybe he came up and gave me a flying drop kick and he's stationary. Then that's 0, his final energy is 0, and his initial energy is something, that would be negative. So if Miles' delta E is negative, that means he has done the work. Does that make sense? Yeah. So it depends on where, if you are getting energy, then work is done on you. But if you're losing energy, then work is done by the system. Okay? So it just depends on, and you've got to look at two different systems. You could look at me, look at my delta E, look at Miles' delta E. If his is positive, mine must be negative. And vice versa. If Miles is negative, then mine must be positive. So it's really showing where the energy's going. Okay? And we'll learn about the conservation of energy. If Miles loses 500 joules in giving me a drop kick, then I must have gained 500 joules. I can't gain 600 if Miles only gave 500. So we're looking about conserving energy. You can't just create energy out of nowhere. It can be transferred. Yes?
What if the amount of work acting on each other is equal?
Well then, his must be positive, mine must be negative. Yep, so, but it depends. If I'm gaining energy, it must be because he's losing it. Okay? We can't both gain energy. That violates the rules. That would be like Miles coming to drop kick me speeding up and him speeding up. You would see this when we both go flying.
But if you're both running at each other, hit each other, you're both flying down.
Ah, very good. Now this is a very painful example. If you run into each other, we've both got energy. Yeah. Bang, we fall down. Well, we've both done work, but where has it gone? It would have gone into smashing all of our muscles together and breaking capillaries and making bruises and sound and heat. And if it's enough energy, you might break your nose and an arm might get broken. The energy has to go somewhere. Yeah. And that's why it's dangerous doing that. Yes?
If you say you have Miles, you would go steal a boost to keep
You're right. So that's why, this is why this term, I can still have some final energy. You're right, I might still be able to follow through and have some residual energy, in which case that I might have a small number, subtract a big number, and that energy is still negative, and that energy is the energy that you got. So you're absolutely right. I just went for a very simple example of like two billiard, go with a billiard ball, a pool ball. You get that. In which case, he's stationary, he was, that's just a nice easy. But you could get that kind of scenario, okay? Let's keep going. Consider this, my wonderful drawing, and then I come over here and I always do this example. Imagine if I apply a force of 1,000 newtons, which can be done. I could put a force, like a set of scales here, and I can push on the scales, and it might read 100 kilograms, which I could then convert and say, well, it's 1,000 newtons. I could be standing here for the entire lesson, exerting 1,000 newtons on the wall. It'd be a very stupid lesson. At the end, I would be exhausted, I'd be sweating, I'd be tired, my muscles would all be sore. But have I transferred any energy to the wall? No.
The muscles.
You just read that.
No.
I added this year. Normally that would have been blank and I would have forced you all to scribble it down.
I didn't actually.
Oh, yes, my muscles have done work, but internally. So you've got to be careful of how the question is worded. Have I done work? Yes. I may have burnt 1,000 joules. Have I done work on the wall? No. Has the wall done work on me? No. You've got to be careful on the wording. Now, we go back to the idea of the force has to act over a distance. So in this scenario, could you, and I haven't written it there, but could you please write S equals 0, W equals F times S, so there's no transfer of energy. Okay? But if we could look into all of my muscles which are contracting and flexing, you could look at all the fibers, the muscle fibers. What they're doing is they're applying a microscopic force over a microscopic distance. So every time you contract your muscle, I want you to imagine a little bit of friction is made, force times displacement. So your muscles apply a force over a distance, and they're all doing work. And again, if you could watch this action with an infrared camera, you would see hot spots. Your muscles would start to get warm. And then your body, your blood would try to move this heat around, and I'll start to sweat and pant. But your muscles get warm. So the energy is, you are transferring sort of chemical energy into heat, okay? But you're not doing any work on the object because you're not moving it. If, let's just say I pushed it this way and all of a sudden there was this massive crack and then the wall, this whole part just went sailing over, you'd say, yes, I can see that it has now gained energy. Work is being done on the wall because it's speeding up. But that's not the case because it doesn't move. Yes?
What happens if you're pushing on the wall, it doesn't start moving, and then after like time it starts?
Well, it's only when it moves that I can say I'm doing work on it. So I could be there pushing for a minute, nothing, and then all of a sudden crack, and then vroom, and then as it starts to move, I can start saying, all right, I'm actually transferring energy to it now.
What if it doesn't completely fall over and stops there?
Well, it's just whatever the force is multiplied by the distance. The next example, these are two examples where no work is done, okay? So the next example is if I carry a boombox on my shoulder, which I don't have my boombox, but you know what a boombox is? It's like your old school speaker. Now, in order for me to keep the boombox from falling, I have to apply an upwards force. I would have to apply 100 newtons upwards. So literally, my muscles on my shoulders must be applying 100 newtons upwards. Now, let's suppose, that's 100 newtons? Yeah. Let's suppose I walk for 50 metres. Miles, what are you looking at?
I was just trying to see what it
Okay. It doesn't go anywhere. Don't worry.
Now, what I want you to, okay, imagine that I'm not speeding up and I'm not slowing it, because as I speed up, then yes, it does gain energy. So just imagine I'm walking at a constant speed, 50 meters. But I'm applying a force that way, but I'm moving that way. And this is an important thing. The force has to be in the direction of the motion in order to transfer energy. So another question is this gaining any energy as I'm walking like this? No, it might have a little bit of kinetic energy. It might have a little bit of potential energy because it's mgh, but none of those values are changing. It's not gaining, it's not losing any energy. Okay, so that's another example where no work is done. If I suddenly decided to shot put the boombox and apply a force that way, then there is a force that's in the direction of the motion, and then we could say, right, the force that you apply in the direction, it might be a meter. If I can shot put it, my arm applies that force for about 80 centimeters, then we could determine how much energy I've transferred to it. Okay?
And would you include like bearing?
Very good. You've just reminded me of something very important. Can you please add another note at the top here? And while we're here, let's fill in that work is now measured in joules and energy is also measured in joules. And Jack has reminded me, you need to know that energy is scalar. It does not have a direction. So we can't say, if I shot put the boombox, we can't say that it's got 500 joules north-northeast. No, it's just 500 joules. It's just the magnitude. It's just the amount. No direction. Okay? Here is an example where force is done. Okay? So if I wanted to lift this object, I would need to apply 100 newtons upwards. So let's suppose I lift, instead of carrying the boombox, let's suppose I lift the boombox upwards. I would apply a force of 100 newtons over a distance of 2 meters, in which case I could say work equals transfer of energy okay? Okay, so again, by doing that, the person has literally lost 200 joules of potential energy by his muscles converting sugar into, your mitochondria doing all that stuff in the cells. I don't know, it's biology. You start off with a big store of chemical potential. The food that you ate last night and breakfast this morning is sitting in your muscles just waiting to, and then you can sort of do this and you're converting chemical energy into kinetic energy. It's the same with where did that energy come from? The box now has 200 joules. It must have come from somewhere. It's been sitting, waiting in your muscles. Okay, you're converting chemical energy into mechanical energy. So again, there's two ways to look at this. Work is done on the box. The box's energy changes by positive 200. It gains. The person does the work. So their transfer is negative. They've lost it. Okay? It must have been there to start with. So that's why chemical energy is sitting there. You all have millions and millions of joules of stored potential energy. Okay? You could go outside and run around and play sport for 2 hours. You start to get tired. So you replenish your energy stores. You have lunch, and then you're building up your potential energy stores again, so you can do it all over again. Run around and throw your arms around. you're always putting energy in so that you can then expend it. This probably won't be part of the course, but this is the idea of we only want the force that's in the direction of the displacement. I've misspelt the word parallel, but if I said, here is our force F, we only want the direction of the force that's in the direction. So if I was to apply a force to this mass, let's suppose this is, this could be a mass on trolleys, right? And as we push it, it starts to speed up, okay? And this is where your trigonometry and your geometry is important. We need to determine how much of that F arrow, or that F vector, how much of that arrow is acting horizontally. So obviously we need to know the hypotenuse, we've got that angle, we're trying to find the adjacent, so what do we use? SOHCAHTOA? What do we, not tan. We've got hypotenuse and opposite, what do we use? Adjacent, sorry. We've got adjacent and hypotenuse. What do we use? We could say that fx is f cos theta. So W, no, I don't think it's in the test. But that's what, so basically this component, this upwards component is wasted. It doesn't do any work. It doesn't transfer any energy to the mass. If the mass just simply moves horizontally, then it's only this component that's transferring energy. This might be wasted. All this is doing is lifting the mass up a little bit, but not off the ground. It's just going to reduce the normal force. If this component was greater than the weight force, then yes, that thing's going to get flung up into the air. But for now, we would just say, it's a bit silly. If you want to push something, the best way to get it moving is to push it in the direction that you want it to go. There's no point going to the prowler sled in the gym and applying a force downwards, because then you're just pushing the prowler into the ground. And it's silly to try and push it vertically or diagonally upwards, because you're wasting, you only want the force that's in the direction of the motion. So it makes sense, if you want to move something, you push it in the direction you want it to move.
If they wanted it to move in the other.
You don't, it's too heavy. It's a prowler, too heavy. How much time do we have left?
15 minutes.
Awesome. We're going to look at some equations. Now, you've already learnt some equations of energy, potential. Does anyone remember the potential energy equation?
Yeah.
EP equals? No? Do you remember the energy stored due to its state or position? No? All right, well, we're going to derive it.
Times mass over time.
No. We're going to derive it. Don't write that there yet. I thought someone might have remembered it. Now, gentlemen, an object's weight can be written as mass times gravity, and that's the force due to gravity. Now, if you wanted to lift this object, you would have to apply a force that was equal and opposite, upwards. So imagine, again, we've got 100 Newton weight. If I want to lift that object, I would have to apply 100 Newtons upwards to get it moving upwards. Okay? In fact, truth be told, I'd have to apply a little bit more than 100 to get it going. So a little bit more to get it going, and then a little bit less to stop it. But on average, I'm applying 100 Newtons as I lift this object over a height h. So I would say the equation is still work equals F times S.
Wait, is something's mass its weight? Complete weight after gravity?
An object's mass is how much inertia it has.
Yeah.
It's weight divided by gravity. So an object's weight is mass times gravity. Okay? Now, I've just told you that we can write the force as mg, and now the distance that it's acting, let's call it height, which is the vertical distance, mgh. So I would say the work done is the transfer of energy which can be written as mgh. So I would say if I lift that object a certain height, I do work on it, and the energy that it receives can be quantified, it can be calculated as mgh, mass times gravity times height. That's how much energy it has. It only depends on what its mass is, the gravitational strength, which on Earth is 9.8, and the height. Now again, we call that potential energy. So EP equals mgh. That is the energy an object has due to its height above the ground. And we are still dealing with m is mass, and it's always in kilograms. G is gravity, and it's always in meters per second squared. And h is height, always in meters. So have a look at that, guys. It's all the SI units. It's kilograms, meters, and seconds. No more kilometers, no more hours, not centimeters, it's not grams, it's the SI units for mass, distance, and time. And could we just add, you would have probably written this down in year 8 or year 9. We can say, where's my text box? There he is. EP equals, and I'll just make it red. Potential energy due to an object's state or position. Okay? Due to that object's position above the ground, it has the ability to do work. It could fall back down. Okay? Going back to that first example, 100 newtons, and we lift that 100 newton weight 2 meters up, it's got 200 joules of potential energy. It's stored there. It has the potential to do work. It could fall back down and crash back to the ground and make a lot of heat and sound and pain. Okay? So that's our first equation. Does anyone remember that now that I've spoken about it? Yeah? Mass times gravity times height. Next, so that's if the object, the force that we act on, if it is the weight force, then we do work and the energy goes into potential. Let's go to another scenario. Please, Miles, keep your voice down. This one's a little bit trickier to show, but could you just please write? If an applied force acts, then the object is going to accelerate. Okay? We would say it gains kinetic energy. And there is an equation, and I'm just going to write it for now. EK, it's a half m v squared. Okay? So that is our equation for kinetic energy. It doesn't depend on gravity. It's just the mass of the object and how fast it's going.
Is that the letter V after M?
Yep. Okay? So if we had an object on wheels and we apply a force, you would say from Newton's second law, it accelerates, it gets faster. And at the end of that S, it's going to have a certain speed, and now it's got energy of movement. Now this is extension. I'm going to just show you the derivation. You don't have to worry about it. There is an equation that relates velocity to the initial. It's v squared equals u squared plus 2as. This is an equation that relates an object's final speed to its initial speed if there was an acceleration acting over a distance. This is one of the year 11 equations. This is, you guys didn't really have to worry about this equation. We can rearrange for A. what I would do is I would subtract u squared from both sides and then divide by 2s. Okay? Now that's A. From Newton's second law, F equals ma, I could then write that as m times by this. That's ma. Okay? So mass times acceleration, and I'm just expressing acceleration as a different kind of thing. And then, from work equals the transfer of energy equals F times S, that's now F, so I'm going to copy that again, all right? And I'm going to write it over here, m outside of v squared take u squared over 2s times s. Well, you've got a multiplication and a division of s, and this simplifies to m outside of v squared take u squared over 2. Or you could write it as mv squared on 2 minus mu squared on 2. Or we could write it as a half mv squared minus a half mu squared.
Do we need notice?
No. That is your EK final minus your EK initial, which is your change in energy.
Oh my God.
Okay? So, hold on. Hold on. If the let's just say if the object was stationary, u equals 0, v equals question. Hold on. If the object was stationary, if it was initially stationary, then have a look what happens to the equation. If u equals 0, that whole term goes away, and we're just left with this expression that the work done can be quantified, can be calculated and equated as simply a half mv squared. Okay? And that's what we call kinetic energy. You do not have, the year 11s don't even have to worry about, this is too crazy for year 11 physics. We'll just say, you need to remember this equation. Due to an object's speed, it will have kinetic energy. Okay? Now, obviously, we can scribble. But if an object already had some initial, let's suppose it was a car cruising along, and then it stomps on the accelerator, and it accelerates up to a final speed, you would say that the difference in energy is final minus the initial. Let's say it started off with 1,000 and it ended up with 10,000. Then the change in energy is 10,000 minus 1,000. It's positive 9,000. 9,000 joules of energy. Work has been done on the car. Where did that energy come from? The motor. How did the motor get the energy? Chemical energy. That energy was sitting in the petrol tank in the form of petrol. And then it gets pushed into the motor, add some air, add a spark, boom, we get that 9,000 joules. No different to Will Davidson sprinting out of this classroom in about 5 minutes. You go, well, Will had 0 energy, and then he sprinted out and suddenly has, where did that energy come from? Sitting in his petrol tank. His muscles just have all of that energy stored, waiting to be released. Okay? Now how much time do we have?
5 minutes.
5 minutes. I'm going to give you 5 minutes to just chillax. Because you've been... Sorry, I only see you as a student.